Hey guys, Mr. Martin back here today with today's lesson on how to prove triangles congruent by ASA and AAS. Those two abbreviations, of course, referring to angle side angle and angle angle side. Let's get started. All right, let's remember that activity that we did in class where we tore some corners off of a triangle. We're going to do something similar to that again. Suppose you tear two angles out of a piece of paper and place them at a fixed distance on a ruler. Can you form more than one triangle with a given length and two given angles as shown below? So we've got the two angles that we tore out, okay, and we set those, in this case, it's about 6.5 inches apart from each other, or at least the vertices are 6.5 inches apart from each other. The question is, can you form more than one triangle? Okay? Let's investigate that a little bit. Before we investigate that, I want to give you a definition. The definition is the included side. It's going to sound very much like the definition of included angle. In a polygon, the side connecting the vertices of two angles is the included side. Okay, so if you remember from before, the included angle was the angle between two sides of a triangle or formed by two sides of a triangle. Now we're talking about the included side, which is now in between the two angles. So in our previous example with the ruler, it's the side that's parallel to the ruler. Well, given two angle measures and the length of the included side, you can make only one triangle. So all triangles with those measurements are congruent. So that brings us to what's called the angle side angle, or ASA, congruence postulate. Very simple. Just like we said, if two angles and the included side of one triangle are congruent to two angles and the included side of a second triangle, then the two triangles are congruent. This is kind of like a shortcut because if you remember before, there's 6 pairs of angles and sides. We don't have to prove all 6 pairs are congruent. If we can prove that two angles and the included side are congruent, we're done. We know the triangles are congruent to each other. So in this example, we've got angle A congruent to angle D. We've got side AC congruent to side DF. And then we've got angle C congruent to angle F. That, of course, is the angle, the included side, and the angle. So triangle ABC is congruent to triangle DEF. Let's move on and talk about the example using this information. Can the triangles in this picture be proven congruent with the given information? So look at what they give us. It looks like they give us two pairs of congruent angles. We've got this angle up here, congruent to this angle down here, and likewise this angle down here is congruent to the angle up there. You can even remember, if you remember, those are alternate interior angles, and I know it's not asking the question, but those lines have to be parallel. Okay? But do we have enough to prove that those two triangles are congruent? Well, look at the middle side. Look at the included side, the side in between those given angles. Obviously, those two triangles share that side, so that side is congruent on each triangle. So I think we have enough. Two pairs of angles and their included sides are congruent. Therefore, the triangles are congruent by the ASA congruence postulate. Let's move on to the next theorem. This theorem is the angle-angle-side theorem. It's going to sound just like the angle-side-angle theorem, but the difference again is that this is a non-included side. So now we've got two angles and a side that is not included. In other words, not the side in between. On the angle-side-angle, it was AC and DF, the side in between. But now we've got BC and EF. So now we know those are the sides that are not included. Okay? So it says very simply, if the two angles and a non-included side of one triangle are congruent to the corresponding non-included side and angles of the second triangle, then the two triangles are congruent. Okay? That should sound a lot like the postulates and theorems that we did from the previous lesson. Let's look at an example using this information. Okay? This is actually something that I know very well. It's a foul pole down the left field line at a baseball field. And it's got a screen up on it, and it's got some triangles there. I'm wondering, are those triangles congruent to each other based on the information that you've been given? Okay, so it looks like we've got an angle congruent to another angle. So we've got the angle congruent to the angle, and we've got a side congruent to a side. So we need another angle. Well, you remember from the vertical angle congruence theorem that all vertical angles are congruent to each other. Okay? So we do have, in fact, let's put 2 arcs on there because that's not necessarily the congruent to the original angle. Okay? So now we've got, in fact, angle, angle, side. So we have 2 angles and the non-included side. Okay? So we have enough to prove that these triangles are congruent by the angle, angle, side congruence theorem. All right. I'll introduce you now to a third way to do a proof. You've written 2-column proofs and paragraph proofs. Let's talk about a third way to write a proof. It's called a flow proof. A flow proof uses arrows to show the flow of a logical argument. Okay? If you've ever seen a flow chart, it has boxes and then arrows leading from one box to the next. This is something very simple. Okay? Each reason is written below the statement it justifies. Before, in the 2-column proof, we wrote the statement next to it. This time, we're going to write the reason below the statement. Okay? Let's take a look at an example. Okay, so I want to prove the angle-angle side congruence theorem by using a flow proof. Okay, so let's review what we have here. We've got angle A congruent to angle D. Okay, we've got angle C congruent to angle F, and we've got the non-included side BD and EF, or one of the non-included sides, BC and EF being congruent to each other. So we want to prove that those 2 triangles are congruent. But we don't know that the angle-angle side congruence theorem exists yet, so we want to think about a way to prove it without that. So we need to figure out a way to get that other angle. Okay? So let's take a look at the flowchart proof. If we can get that other angle, meaning namely angle B congruent to angle E, we could use now the angle side angle side angle congruence postulate. Okay, we know that one is accepted without proof. So let's take a look at the flowchart proof. Okay, so they gave us 2 angles, and we know, thanks to the third angles theorem, that the other angle must be congruent. If 2 angles of a triangle are congruent, then we know the third angle is congruent to the third angle of the other triangle. So we now know that angle B is congruent to angle E. So now we have enough because we now have an angle, oops, there's the angle up there, and a side that are going to be congruent to each other. Okay, so let's get rid of that because we know that that is not the right letter there. We have an angle, a side, and another angle. Okay? So we have now angle, side, angle. So we have just proven that those 2 triangles that originally had angle, angle, side marked are actually congruent using angle, side, angle. We got that third angle, so now the side that was given is an included side, and we can use ASA. All right, let's move on to the last thing I want to talk about in this video, and that's actually a real-life example. That example is one of the coolest examples I've seen in using these theorems. I don't know if you know it or not, but the Forestry Service uses fire tower lookouts to watch for forest fires. They're just these big, tall towers in amongst the trees. Okay? When the lookouts spot a fire, they measure the angle of their view, and then they radio a dispatcher. The dispatcher then uses the angles to locate the fire. I always wondered how they found out where fires were in the forest. Well, I want to know how many lookouts are needed to locate a fire. Let's take a look, and let's use geometry theorems. So there's your picture. Okay? You can see we've got Tower A, and we got Tower B. And then we got, we got a fire going on right here. Big time fire. Okay? We got to figure out where that fire is so we can tell the dispatcher where to send the trucks. Okay? So the locations of Tower A and Tower B and the triangle form, and the fire form a triangle. So you can see it on the diagram here. The view of the person at Tower A is looking out across this side. The view of person in Tower B is looking across that side. And the fire itself forms the third vertex of that triangle. Okay? So, question, if we know this angle right here that person A is seeing the fire at, and we know this angle that person B is seeing the fire at, and we know the distance between those two towers, do we have enough to prove that those triangles are congruent? Guess what? The answer is yes. The dispatcher knows the distance between towers A and B and the measure of angle A and angle B. So the measures of two angles and the included side are known. So by the angle side angle congruence postulate, all triangles with these measures are congruent. Therefore, the triangle formed is unique and the fire location is given by the third vertex. So the answer to the question is we need 2 towers and we will be able to locate the fire. I think that's a pretty cool example of actually using this stuff in the real world. Well, there you go, you guys. There is the lesson, and make sure you got notes and questions for class, and I'll see you guys in class. Have a great day.